it is my honor to present our work here. Our work name is a 4-arm electrically small omnidirectional CP helical antenna and its expansion as a compact and highly efficient dual CP array. Next, I will present it in 4 parts, respectively. The first part is the background and motivation of the design. Firstly, we know that OCP antennas are attractive in many wireless applications as it can provide a 360-degree radiation coverage in the azimuth plane and avoid the polarization mismatch issue that might be arose in linearly polarized system. In general, 3 popular design methodologies have been adopted to achieve OCP radiation characteristics. However, most reported antennas suffer from larger sizes and more complex structures, so the goal we are trying to achieve is a simple, electrically and structurally compact antenna. The second part is that we are going to design the principle of operation of the OCP antenna. We were using the most common design approach, which is to have a pair of parallel electric and magnetic dipoles with a 90 degrees phase difference. The third part is the antenna design process. In our work here, we start from a conventional normal mode helical antenna. It has a simple and compact structure. And if the specific condition is met, OCP radiation will be produced because a balanced pair of an electric dip alley from the vertical currents and a magnetic dip alley from the loop currents is formed. Unfortunately, this OCP mode is rarely used because the antenna suffers from an extremely low radiation resistance. In previous studies, an effective way to increase the input impedance of an antenna is to increase the effective current density of the antenna, in other words to introduce more in-phase current paths. Most of the previous work has done this operation by cascading the antennas, but it greatly increases the antenna size. Therefore we try to use near-field coupling for this purpose. With the introducing of parasitical helical wires, we found that the radiation resistance has been substantially enlarged and the OCP radiation performance becomes better. Next, we also simulated the surface current distribution of the antenna in a period of time when the driving element is excited. We found that the currents are approximately equal in magnitude and phase on the 4 helical arms. This means that the total radiation is the superposition of the radiated fields from all 4 identical helical currents. On this page, we displayed the final model and parameters of the antenna, and we can see that the structure of the antenna is very simple, and is physically and electrically ultra-compact by simply introducing 3 additional parasitic helices. Based on the proposed OCP helical antenna, we designed a dual OCP antenna array with compact size and highly efficient. We can see that the simulated and measured results agree very well. In conclusion, it is clear from the comparison table that the designed antenna unit has very compact size. It can also be seen from the antenna array performance comparison table that our array is the most compact and has the highest realized gain. Thank you.
Hello, everyone. It is my pleasure to introduce our research on a wideband dual circularly polarized series fed corner-truncated patch array using coplanar proximity coupling. The geometry of the proposed wideband proximity coupled series fed dual CP antenna is shown in this figure. It is composed of a cross-shaped arrangement of corner-truncated patch array serving as the radiator, a folded microstrip line, and 2 tapered microstrip lines acting as the feeding structure, and a soft surface structure for radiation pattern improvement. Compared with the existing works in series fed dual CP antenna designs, the contributions of this work are summarized as follows. First, the corner-truncated patch array is for the first time used in designing an proximity-coupled series-fed dual CP antenna. Besides, it effectively resolves the problem of narrow operating bandwidth for the previous single-layer series-fed dual CP antennas, while maintaining a high antenna efficiency simultaneously. Furthermore, the proposed antenna achieves stable boresight radiation across a wide operating bandwidth, effectively mitigating the common beam deflection issue in previous coplanar single-layer series-fed dual CP antennas. Compared with the existing series-fed dual CP designs, The proposed design achieves attractive features of simple structure, wide operating bandwidth, high antenna efficiency, and low cost. This page shows the design evolution and operating mechanism of the proposed antenna. At first, the proximity-coupled series fed technique has been introduced for the Parasitic dual CP operation at a lower operating frequency, which is indicated as antenna 1. Then, we introduced the inner patch group and corner-truncation, which are indicated as antenna 2 and antenna 3, respectively. By this way, the coupled power for the 4 outer patch group elements becomes more balanced, as shown in the figure of current density distribution. Thus, the operating bandwidth has been improved in antenna 2 and further in antenna 3. At last, in proposed antenna, a soft surface structure has been incorporated to improve radiation pattern at a higher operating frequency. When utilizing the soft surface structure, the surface electric field is predominantly confined within the structure itself and exhibits a relatively uniform distribution. The proposed wideband proximity-coupled series-fed antenna has been simulated, and a prototype has been fabricated and measured. Here are the simulated S-parameter and axial ratio when port 1 is excited. Taking into account the 10 dB impedance bandwidth, 15 dB isolation bandwidth, and the 3 dB axial ratio bandwidth, the operating bandwidth of the proposed antenna is 18.5% in experimental measurement. The radiation performances of the antenna are shown in this page. It can be seen that the proposed antenna maintains stable Parasitic CP radiation characteristics at the 3 frequencies across the operating band. Across the operating band, the measured realized gains range from 6.82 to 8.48 dBIC. The measured total efficiencies range from 74% to 85.5%. More details can be found in the references. Thanks for your listening.
In this video, I'll briefly introduce the design of a high-performance dual-polarized tilted beam parasitic array antenna. There are 2 main methods to achieve dual-polarized tilted beam radiation. The first is using dual-polarized elements with a complex feed network, but these antennas are typically large, complex, and costly. The second method uses parasitic coupling in a Yagi structure, which usually works for linear polarization but struggles to achieve good dual-polarized tilted beam radiation. The main challenges are maintaining high polarization purity and ensuring strong isolation between ports. To address these, we've designed a high-performance, single-layered, dual-polarized, tilted beam parasitic array antenna. This design effectively resolves issues like complexity, low polarization purity, and poor port isolation. Our design uses a circular dual-mode resonator as the modulation unit for dual polarization. The polarization directions of the 2 orthogonal modes in the ARR depend on feed point positions. When these feed points are symmetrically placed at plus or minus 45 degrees, a pair of 45 degrees plus or minus linear polarization degenerate modes can be excited. By treating J plus or minus 45 degrees as a vector sum of J1 and J2, and ensuring their coupling strengths are equal, the array's polarization direction remains at plus or minus 45 degrees. The edge spacing G is key to achieving this balance. Once the modulation unit and G are set, we calculate the tilt angle and structure parameters based on refractive index modulation. According to the ARR's field distribution, the zero field regions of the 2 modes are separated by a quarter wavelength. This means 2 feed points, a quarter wavelength apart, naturally provide good isolation by being in each other's zero field region. Our final design consists of 5 dual-mode resonators with refractive index modulation and a pair of bent microstrip lines for feeding. The bending angle improves port isolation and cross-polarization purity while significantly affecting phase. With quantitative coupling control, the surface currents on each resonator align along plus or minus 45 degrees, achieving high cross-polarization purity. Simulation and testing results show fractional bandwidth for the 2 ports at 12.3% and 11.6%, with gains above 10.5 dB and overall efficiency over 92%. Radiation patterns across different frequencies confirm a high XBD level with a stable tilted beam fixed at 45 degrees. In summary, compared to existing solutions, our design solves the challenges of dual-polarized parasitic arrays without needing extra feed networks. It offers wide impedance bandwidth, high port isolation, and maintains high cross-polarization purity even with large beam tilt angles. With its compact, single-layer design, this antenna is ideal for applications like base stations and similar scenarios. Thanks for listening.